আমার কথা শুনতে পাচ্ছো?
Yes, ma'am.
So we have discussed this basic phasor diagram and characteristics of cylindrical rotor and salient pole machine. Now, while describing the machine performance, we have defined the synchronous reactance, and we have seen that synchronous reactance for cylindrical rotor as the air gap is constant and the reluctance offered to the armature reaction field is independent of the position of the rotor and the armature winding. So we have only one synchronous reactance. But however, in the in case of salient pole machine, the reluctance offered to the flux path along the direct axis or the polar axis and the interpolar axis or the quadrature axis are widely different. So two synchronous reactances were introduced. One is the direct axis synchronous reactance and the other is the quadrature axis synchronous reactance. Now, these synchronous reactances defined are sufficient for describing the machine under steady state condition. But under short circuit condition, some other factors comes into play and these synchronous reactants are not sufficient. Now short circuit or synchronous machine fault, those we are not discussing in this syllabus, that will be discussed in details in your power system course, but I will just describe in very brief what happens during short circuit, why we require different synchronous reactances and how to measure those synchronous reactances. So short circuit condition, what happens, there can be always a fault, there can be a sudden short circuit of the synchronous generator when it was running with full load and full excitation. Now, at what point of the current and voltage waveform and at what position of the rotor and stator windings particularly short circuit happens, that have a profound influence on the machine, that on the profound influence on the short circuit current, what short circuit current will flow and what will be the behavior of the machine. And this behavior of the machine on the short circuit condition is very important from the mechanical point of view, because high forces are developed during short circuit because the current is very large and the force developed is square of the current, proportional to the square of the current. So the machine should withstand this high mechanical stress. Now, in the armature winding active portion, active conductor portion, which is embedded in the iron supports the winding, so it is mechanically strong. But for the overhang region, that is at the end connections, those portion that iron support is not there, so mechanical bracings and support should be provided so that the winding does not get deformed during short circuit. Now, the train of events, what happens after short circuit fault, depends on exact instant in the cycle when the short circuit occurs, the load and the excitation of the machine exactly before the short circuit, the type of short circuit, that is, we can have a single phase to ground fault, two phase short or three phase dead short circuit. So it depends on which type of fault it is, because the current magnitude and the form will depend on that. Then the constructional feature of the machine also is important, because that will affect the leakage and damping. The actually the shorts this total uh, the short circuit the time of the short circuit just after the short circuit is divided into three regions. The first one or two cycles, that condition depends on the flux linkage, because the synchronous machine is predominantly inductive, so the machine will try to keep its flux linkage stator and rotor flux linkage is constant. So first two cycles will be affected by that, so that the current in the damper winding, in case of the cylindrical rotor, the current in the solid rotor winding, then will try to keep the flux linkage of the machine constant as the just at the moment just before the short circuit occurs. Then after one two cycles, that interval of time, the system is there as inherent damping, so subsequent cycles, that damper parts and those current will die down, and this there will be a few transient cycles over which the current will subsequently gradually decrease. Then finally there will be a steady short circuit condition, that is the current magnitude will be large, but that will be steady, not varying with that magnitude not varying with time. Now the obviously that generator, that we when the machine is operated, we never go up to the up to phase 3, that is machine is disconnected. In the first two cycles are subtransient, then the transient, when the magnitude of the short circuit current is decaying due to the damping of the inherent damping of the system. So in the transient region itself, the machine is disconnected. Now how the in that short circuit condition is affected by the initial condition, that we can explain in a very briefly. That is mainly can be explained by the theory explained by theorem of constant linkage. That is, it's in a RC RL network, if it is there is no source, then Ri plus Li dt is equal to 0. Li is the flux linkage, so L equal to 0, because it is short circuit, there is no linkage. Now if the resistance R is neglected, that gives you d Li dt is equal to 0. So that means the system will try to dli, that is Li is phi, so d phi dt is 0, so rate of change of flux should be 0, so the system will try to keep the flux constant if it is a if the resistance of the system is negligible. Now the synchronous machine, we have seen that the resistance is very small compared to the inductance, so it is basically a predominantly inductive circuit. Because of that, when the short circuit happens, the machine will try to keep its flux linkages constant. Now what happens if the machine try to keep its flux linkage constant? Now let us consider two extreme conditions. Say consider short circuit at zero linkage position. That is, if just before the short circuit, I have considered a two-pole machine, that is simpler to understand. Two-pole, and this is a single-phase machine. We are not going into details of three-phase short circuit and other things. Just to explain why we require subtransient and transient reactances. So this is a zero linkage position. So if the short circuit occurs here, so this is the instant of short circuit. So at this position, the linkage of this conductor is zero because it is the this winding axis is perpendicular to the field axis. Now, just after one-fourth revolution, now this is I'm considering the anti-clockwise direction as positive. So the north pole will come here. So north pole is here, south pole is here. So your field excitation is still there. It is not disconnected. So this field distribution will be like this. So what happens here? The link, this conductor linkage was zero, but here now the conductor linkage is no longer zero. This is maximum position. The field axis and the winding axis is coincident. So current will flow in this armature conductor such that it can keep the linkage of this conductor zero. So the current direction will such that is here it is the main flux created is in this direction. So current should be such that it creates a field in the opposite direction so that the immediate vicinity of the conductor, the flux linkage is zero. So as the rotor moves through another one-fourth revolution, that is not comes here. Now again the field axis and the coil axis, armature coil axis are perpendicular, but now it has reversed. So, but the conductor linkage has become zero naturally. So the current will die down. So the armature current for this position it will become maximum. Again in this position it will die down. As further it goes, it will be maximum in this direction and die down. This way the armature current will flow. I have not considered initial armature current flowing. There was no initial armature current. So what happens in the field now under normal steady state condition? That field is not affected by the field current is not affected by the armature current. So field is excited through a DC exciter, so it has constant current. Now, what happens uh, when this short circuit appears? Now this conductor, this for this figure, that this was the steady state field current flowing. Now for this second figure, now the armature has started flowing a current in the armature so that it will create a field. It will say this was not here. This is create a field to oppose the field created by the field winding. So the field winding current will increase because the flux linkage of the field also should remain constant. So field winding current will increase so that the flux linkage of the rotor remains constant. So field winding current will increase. Now when this armature current dies down, those increase in the field current will die down. It will have a constant value. Then again, as the armature current increases, then field current will increase. Armature current increases in the reverse direction, which is this is AC, but the field it will have the same direction. So this will be the field current profile. So what happens? This field current will now also have some way. This not remain constant. It will be vary like this. Now, what happens if the initial short circuit, instead of a zero linkage, we had at the maximum linkage condition? That is the armature winding and the field winding axis are coincident. Now, here also initially I am considering the armature is not carrying any current. Now, for this is for the initial instant, this is the flux distribution. Now, as the rotor moves through 1/4 degree, so south will come here, south will come here. Now, what happens for this position? The normal linkage of the armature conductor has become zero, but the armature will try to keep the linkage intact. This was the maximum linkage position. So armature will carry current so that the linkage can be uh, kept constant. Now, after another one-fourth revolution, now the rotor position has reversed. Now this south, this is north. So the field created by the rotor has totally reversed. So the armature will draw more current so that it can keep its linkage equal to this initial position. Though, so like these two figure, you can see that here it was the maximum in position 2, then it died down, but here the current will go on increasing and it will be maximum in position 3, then only it will die down. So you can see the form of the curves are also different. So what happens to the field? Similarly, field will also keep to try to keep the rotor flux linkages constant. So in this position, as this current is flowing, so field current will slightly increase. But in this position, actually, this field and the field created by the field winding are just reverse. So the field winding current will increase quite a lot more than this, so that it can keep its flux linkages constant. So this will be the form of the current flowing through the field. So this is the this happens for one or two cycles, then the thing damped down. Now this is the figure for a transient wave. It is for a symmetrical short circuit. Actually, what will be the whether it will be symmetrical or asymmetrical, that depends on as I told, that depends on the instant of short circuit, then the type of short circuit. This is just an example for symmetrical. It can be asymmetrical also, totally asymmetrical like this, or partly asymmetrical. But it has this steep portion. This is the subtransient. Then this portion is transient. Then this is the steady state short circuit. So the steady state synchronous impedance, what we defined, that is not sufficient to uh, explain the behavior of the machine in the subtransient and transient region. So we require different synchronous machine reactances. So what reactance we define? We define positive sequence reactances, that is XD, XQ, positive sequence is direct axis synchronous reactance, quadratic axis synchronous reactance. Then this is XD dash, direct axis transient synchronous reactance. Quadrature axis transient synchronous reactance. This is direct axis subtransient. It is direct axis quadrature axis subtransient synchronous reactances. The magnitude of different positive sequence reactance depending on the angular position of the field structure with respect to the armature MMF wave, the whether the armature currents are steady and varying. Now, direct axis synchronous reactance XD, we have defined it earlier. That is when the armature MMF wave is coincident with the direct axis, then the reactance offered to the armature flux path is minimum for given armature current. The armature flux has the maximum value. Under this condition, the armature flux linkage per ampere in the armature winding is called the direct axis synchronous inductance LD. So LD is the armature flux into armature number of turns per phase divided by the armature phase current, and corresponding reactance is XT. So this was the position. This was the armature reaction coincident with the direct axis. So this is the flux distribution under. Now, so direct axis synchronous reactance, it will have basically two components, that is the leakage reactance and XMD, or the mutual reactance in the direct axis, magnetizing reactance for the direct axis. Then under steady state, the armature current has no effect on the field current. So field current is treated as a field circuit is treated as open. That is normal condition. The circuit current is not affected by armature current, or armature current is not affected by field current for waveform. So the field current considered open circuited. So the equivalent circuit of the direct axis steady state synchronous reactance can be considered like this. That is, we have the leakage reactance and we have the magnetizing reactance along the direct axis. Field circuit is open. So this is basically XA plus XMD. Now for the transient reactance, transient the first few cycles there will be current in the damper bar, then the damper bar current will die down. That is, damper bar current will die down when the speed again has regained the synchronous speed, but the current waveform has not now still not settled. That is the transient region. So in the transient region, as it is assumed that the damper bar current is zero, but there is still the linking with the field current. So now if the peak of the suddenly in the equivalent circuit we will have XA, the leakage reactance, the magnetizing reactance in the direct axis, and the field circuit will appear to be closed because it will have an effect on the armature MMF. And the flux distribution we can consider like this. That is, this is the MMF wave coincident with the direct axis. Now, in the original uh, field circuit, this was the distribution. Now here, as the current, this current will oppose the try to keep the flux linkage. Consider, it will try to keep the flux linkage of the field circuit. It will depend on, like, considering that initial linkage was, this linkage was zero, so it will try to keep that. So what will happen, the flux path will this flux will not go through the rotor body, it will go like this. So that rotor body, this in the rotor body the flux linkage remains zero, what was previously. So this will be approximate flux distribution. So the what how we define it, we define that the peak of the armature MMF is suddenly applied. It coincides with the direct axis and tends to force the, it was not there but it is suddenly applied coincident with the direct axis. So it forced the flux line through the rotor core. Since the flux constancy has to be maintained, this flux was not initially going through the, this is the flux what we have I have shown is not the flux created by the field body. This is the armature reaction flux. Initially it was not there, we have suddenly applied it along the direct axis. So the rotor will try to keep its flux linkage constant, so it will not allow this flux to go through the rotor body. So for this the field will draw more current so that it can keep the flux linkages constant. So field will appear to be closed. The flux linkage due to varying armature MMF wave cannot pass through the field body. So the flux path is shown in the figures. In the path is largely through air, reluctance is high, and the armature flux is less. Under this condition, the armature flux linkage per unit armature ampere is defined as the transient inductance LD dashed and the direct axis transient reactance XD dashed is equal to twice pi f LD dashed. Now the figure reveals that the armature linkage is much less compared to the steady state condition. In the steady state condition, the armature ABMF is going like this across the rotor body. This is made up of iron, so reluctance is low. But here it is going through much through air, so reluctance is high. So for the same value of the MMF, the flux will be less. So XD dash will be less than XD. So XD dash can be as the field will is linked with the armature, so field will appear to be closed. So our equivalent circuit will look like this. So we will have XDM and XF, say fielding inductance in parallel. This in parallel in series with XA. So XD dash will be obviously less than XD. Direct axis subtransient reactance is this sudden disturbance in the armature circuit is applied along the direct axis. Then what happens for the very first one or two cycles, there will be change in the field current as well as there is disturbance in the speed, also there will be current in the damper winding. So damper winding current will also affect the inductance. So the flux distribution will be like this. That is, in this figure, the damper bar current we have is has died down. So this flux was entering the rotor body. There is going through like this. Then it will going through the air in this region. But in this region, it was going through iron. But when this is subtransient, this damper bar winding current is there, which will again oppose this flux change. So that path will be totally through air. So the path will be totally through air. This path will be like this. So XD double dashed will be still lower than XD dash. So basically we have XMD, XF and XKD in parallel, that is in series with XA. So actually, since the damper bars are near the air gap, the flux lines are forced to follow the leakage path, mainly in the air. The armature flux linkage per ampere, armature ampere under this condition are called direct axis subtransient reactance LD double dash. So XD double dash is equal to twice phi LD double dash. Comparing the flux path, it is seen that the flux linkage is less during subtransient compared to the transient condition. So XD double dash is less than XD dash. So we have XD double dash less than XD dash, which is less than XD. Now, similarly, for the quadrature axis, we will have reactances. Quadrature axis synchronous reactance, steady state. It is that when the peak of the armature MMF wave is coincident with the quadrature axis, then the reluctance offered to the armature flux path is due to the large air gap in the quadrature axis is maximum. For that, for armature currents, the armature flux will be minimum. Under this condition, the flux linkage per unit armature phase current will give you the quadrature axis inductance LQ, and correspondingly we will get XQ is equal to twice pi F LQ. There is no field winding in the quadrature axis. So field winding, there is no point of having field winding here. However, machines which have a continuous damper winding can have a damper winding in the quadrature axis, but It temporary winding there is no current, so in the steady state we will have XA and XMQ, that is the magnetized reactance in the quadrature axis in series. So XQ will be XA plus XMQ as the, and the distribution will be like this. As from the figure you can see that the reluctance is quite high, so flux will be less, so obviously our XQ will be less than XT. And the what quadrature axis transient reactance XQ, that is the armature MMF wave is suddenly applied such that it gets aligned with the quadrature axis. The flux path will be like this because the axes are perpendicular. So initial flux linkage and final flux linkage is not affected. So basically the flux linkage will be like this. So this flux distribution and the flux distribution for xq is same. So basically xq dash is equal to xq. So the transient synchronous reactance xq and the xq dash and the quadrature axis synchronous reactance xq are equal, because in case of direct axis they are different because that field winding was coming into play. They are here in the quadrature axis we do not have the field winding. However, for the quadrature axis subtransient reactance, we will have the damper bars here because the damper bars are normally continuous. So they are in the subtraction condition, there will be current flowing in the damper bar. So the equivalent circuit will be like this: XA in series with X and Q and XKQ. X and Q is the magnetizing reactance in the quadrature axis. SkQ is the reactance of the damper bar in the quadrature axis. Now this is the field distribution. Now initially what was that? It was going like this. Now it will go mainly through air like this. So your we have defined this, that is xt is greater than xt dash greater than xt double dash. We have xq is equal to xq dash. Xq dash is very greater than xq double dash, because this for xq double dash this one the air gap will be quite large. However, if we compare this figure and for the direct axis subtransient reactance for this figure, you see the reluctance are quite different, because here the reluctance was, this air path was longer. Here air path was longer. So your xt double dash is actually less than xq double dash. So your xd is xa plus xmd, xd dash is xa plus xf and xmd in parallel, xt double dash is xa plus xf, xmd and xqd in parallel. Xq is equal to xa plus xmq, and xq double dash is xa plus 1 by xmq plus 1 by xkq. So these are the different synchronous reactances. Then besides this, we will have negative sequence reactance and the zero sequence reactance, because whatever we have discussed, it is considering the supply is balanced. But supply might not be balanced always. If it is unbalanced supply, we know we can divide it into the positive sequence and negative sequence voltages and the zero sequence. So reactances offered to negative sequence and positive sequence are also has to be defined. Now for defining H2, the unexcited field winding is closed and is assumed on the rotor. The field winding is on the rotor. The direction of rotation of the rotor and armature mmf are opposite. So that is the rotor is rotated in a positive direction by a prime mover, and voltage is applied, three phase voltage is applied to the armature circuit so that the rotating magnetic field created is in the opposite direction. That is a negative sequence voltage is applied. Now under this condition, what happened basically, the relative speed between the rotor and the rotating magnetic field will be twice the synchronous speed. So at one instant, the rotor mmf is aligned with the d-axis, and after a few moments, it will be aligned with the q-axis. Then the flux linkage with the rotor is zero. It should, but we have keep the field unexcited, so the flux linkage with the rotor was at zero and was zero, and it should remain zero. So the path is mainly through air, similar to the flux path for xt dashed and xq dashed. That is these two figure. These two figure, that is this is xq dashed, and for xt dashed, for xt dashed, the rotor flux linkage should be zero. It should not pass through the rotor body, so it is mainly through air. So x2 is considered as average of xq dashed and xt dashed. That is x2 is equal to xt dashed plus xq dashed by 2. Xt double dash by 2. Zero sequence reactance. Now zero sequence phasors are coincident. So to get the zero sequence reactance, the three phase armature winding is connected in series, and a single phase supply is given to this series combination. Then the armature flux linkage is produced as shown in the figure. That is, it is connected in series, and the flux linkage will be like this. That is, if it is dot, the rotor will be this is cross, this is dot, this is the induced in the rotor. There is no conductor, there is nothing induced. So the pulsating armature, but this is a single phase supply, so mmf is pulsating in nature. So this pulsating mmf is opposed by current induced in the closed rotor circuit. This circuit are closed. So air gap is, as the air gap is very small, the armature flux linkage per unit armature ampere under this condition is called zero sequence inductance L0. Now these are the typical values of the different synchronous machine in the parameter inductances. Now it actually depend on the type of machine. So for turbo alternator are cylindrical rotor. So XT and XQ are normally we take that equal to the synchronous reactance, which is not exactly equal, is slightly different. That's a slight different will appear because of the slottings, because the field binding is distributed, but actually in the distribution is such that we will create typical fields. So in the position where there is slot and where there is no slot, the reluctance will be slightly different. So there will be slight difference in the values, but almost same. XD dashed and XQ dashed are approximately same, all same. XD double dashed, XQ double dashed, these are the values. So This is X2 and this is X0. For the hydrogenerator, which is a salient pole machine, so XD and XQ are widely different. XD dashed and XQ dashed are also different. Then XD double dashed, XQ double dashed are also different. And this is for a salient pole motor. This is a salient pole generator. This is a salient pole motor. Motor or generator characteristics performance are slightly different, so parameters are also different. This is a typical parameter. These are per unit values, not the absolute values. Now, so we should be able to measure these reactances. Now, XD and XQ we have discussed. That is, XD can be measured from open circuit uh, data and short circuit data. That is, of induced voltage for a particular field current divided by the under open circuit condition divided by the short circuit current for the same field current give you XD. The ratio of XD and XQ is determined from slip test, and from there we can determine XQ. Now, next is that measurement of XD double dashed and XQ double dashed. The circuit is like this. Two of the phases are connected in series and the single phase voltage is applied. The rotor is at rest and the voltage is adjusted to pass sufficient current in the series connected winding. The rotor position is adjusted to get maximum deflection because the rotor is at rest, so there and it is closed by the armature by ammeter. So due to the flux in created by the current flowing in the armature winding, there will be some EMF induced, and that EMF value will depend on the position of the rotor. So we adjust the rotor to get the maximum deflection on the ammeter. The induced current is short circuit field winding is maximum only when the field winding axis is along the direction of the resultant armature direction of the resultant armature MMF wave. Under this condition, the D-axis subtransient impedance XT double dashed is measured. We measured this voltmeter, ammeter, and wattmeter reading. So from there, XT double dashed is equal to V by twice Imax. Twice Imax because the two windings are connected in series. Then cos theta is equal to P by V Imax. So sin theta we get. So the axis subtransience reactance will be ZD double dash sin theta. So we can put the values get from this equation, and we get X double dash is equal to 1 by 2 Imax square root over of V into Imax whole square minus P square. Now this is, however, considering the resistance RA is RA, armature resistance RA. Now if we neglect the armature resistance RA, then sin theta is and RA if we neglect, then and from this same experiment we can determine XQ dashed also, that is rotor is rotated by hand so that the peak of the armature MMF wave coincide with the quadrature axis. This position actually field winding current will be minimum, that field winding armature ammeter reading will be minimum. Under this condition, we can get XQ double dash. Now, this value of XT double dash and XQ double dash are considering resistance. If we neglect the resistance, then approximately XT double dash is V by twice I max and XQ double dash is V by twice I minimum. Negative sequence reactance is taken, one of the method is taken as the average of these two, or there can be other method also. The field winding is short circuited through an ammeter and the rotor is rotated at synchronous speed. The balanced negative sequence, this is from the definition of the negative sequence of Negative sequence voltage is reduced voltage is applied to the armature terminal so that the armature mmf rotates in a direction opposite to the rotor. The applied voltage is adjusted and the meter readings are recorded. Adjusted to have significant current flowing and the meter readings are recorded. So Z2 will be V by root 3I. Uh, this connection is considered. So negative sequence reactance will be Z2 is X2 is equal to Z2 sine theta. Resistance, if it is neglected, X2 will be uh, V by root 3I. For zero sequence reactance, it is from the definition, the windings are connected in series and the single phase voltage is applied. Then this current I is flowing. Then X0, this rotor is shorted and it is rotated at synchronous speed. So X0 is per phase voltage, that is three phases and series. So V by 3 divided by the current I. So this is V by thrice I. Now this connection is only possible if all the six winding terminals are available. It might not be the case. So if only the line terminals and the neutral is available, in that case you can connect like this. The windings can be basically connected in parallel, the three windings, and here we can apply a single phase supply. The field is rotated and it is shorted similar way. So in this connection, only the current and voltage rating will be that is X0 will be, voltage is V and current is I by 3. So this will be 3V by I. Now in the same circuit, instead of connecting ammeter here, if we uh, it is in this circuit is it should that current direction should be considered, that is it should be connected such that they are in parallel, that is all the currents are flowing in the same direction. So if this is uh, not the case, the current it is recording the current flowing through the neutral, then that should be V by I. So this is the basically the definitions, and in the fourth year you have experiments to determine the parameters, including the zero sequence and negative sequence. So I've just described the methods, but when you go for power system analysis, you understand the effect or what is the significance of this synchronous machine, different synchronous machine reactances, when to use which values. So I will stop here today, and then next class I will take on next Thursday, because more or less we have covered the syllabus. So uh, may, not many classes needed. So I will take only class on Thursday.